basically this is the circuit called tank circuit. It can generate the oscillation. It can generate the oscillation if the capacitor is charged by external means, and then we disconnect that source. What will happen? This circuit will start oscillating, okay, and the oscillation which produced by this circuit will be the damped oscillation. This is a limitation. It is giving oscillation but are damped, having constant frequency. So this is basically an oscillator but with limitation. Oscillation produced by this circuit, the damped oscillation, decreasing amplitude. What is the required? The requirement is undamped oscillation. We need undamped oscillation. So with that, this is the basic principle with the condition. Okay, mean if we have to supply some energy continuously to the tank circuit, then we can have undamped oscillation. The tank circuit, like this one, it is used as a feedback network, okay, having inductive and capacitive elements. This tank circuit produces a phase shift of 180 degree, and 180 degree phase shift is produced by common emitter configuration. Okay, transistor now here act as amplifier. It also produces a phase shift of 180 degree. So 180 degree by transistor, 180 degree by tune circuit, total phase shift becomes 360 and applied back to the base. So this is the basic requirement, and energy comes now in phase with the input. Oscillation which will produce now, that will be undamped. The tune circuit or the tank circuit, it gives a phase shift of 180 degree. 180 degree mean like this is the input signal, and transistor gives a phase shift of 180 degree like this, 180 degree. Again, tune circuit also gives a phase shift of 180 degree to this one. Again it becomes like this. So this signal is taken back, and it comes in phase with the input. That is the requirement. This is a limitation of LC element. Okay, they suffer from frequency instability. Poor waveform cannot be used for very low frequencies because they become too much bulky and expensive. So we do think the alternate of LC, that is the RC oscillator. Okay. So a phase shift of 180 degree is obtained with a phase shift circuit. Instead of we are not using inductive or capacitive element, we are using RC now. Then a further phase shift of 180 degree by transistor, so total energy comes in phase. So this is one CR element, second CR, third CR. And you know, if the distance R is varied, you know, each CR gives a phase shift equals to phi, and the value of phi will change if R is varied or C is varied. If R is varied, and moreover if R were reduced to 0, then the phase shift becomes 90 degree. But you know, there is always some R. There will always be some R. So, and adjusting R to 0, it is impossible for the value of R to have the value of R equals to 0. There will be some value of R always. So in practice, our R and C values are such that we have, you know, phase shift by one CR element is 60 degree. Here there are three CR elements, 1, 2, 3, and each CR section gives a phase shift of 60 degree. Transistor itself gives a phase shift of 180 degree. 180 degree by transistor, 180 degree by RC, 3 RC elements, Total becomes 360. Okay. We will use the Cramer rules for calculating the frequency of phase shift oscillator, and we're giving an example here how we apply the Cramer rules, how we use the Cramer rule. And this is a basic by taking an example. Example is that we are having some equations with the unknown parameters x, y, z, and with the help of the Cramer rule, how we can find the value of x or y or z, and x having the coefficient here, x coefficient is 1, y coefficient is 1, z coefficient is 1. Here x coefficient is 1, is minus 2 is 1, x coefficient is 1, here is coefficient is plus 3, coefficient is plus 4. Okay. So here written the x coefficient is 1, y coefficient is 1, z coefficient is 1. Here x coefficient is 1, here minus 2, here 1, then 1, then 3, then 4, like that. That is called T. We will solve first of all T, then Now here, dx matrix. Here, the coefficient of x were not written here, and this column will be replaced by this column. Okay, then it will become dx. Now for dy, x coefficients are here, z coefficients here, but y coefficients were not here, and y coefficients will be replaced by this column. Okay. Now dz, x coefficients there, y coefficients there, but z coefficients missing. Instead of z coefficient, they will be replaced by this column. Right, that becomes dz. Now you can find the value of x, how? Dividing dx by d. You can find the value of y, how? Dividing dy by d. this is an op amplifier, right, having inverting terminal and non-inverting. Non-inverting is grounded, and RF is the feedback register for the op. RI is the input register to the op, because the input is at the negative terminal. Output which the op gives will be out of phase to the input by 180 degree. Now there are three CR element. The C and R circuit, they are chosen such that each gives a phase shift of 60 degree, 60, 60, 60. That becomes 180 degree. So here by CR the phase shift is 180, by op the phase shift is 180. Total phase shift becomes 360. That the total phase shift is 360. That means the signal will be in phase with the input. Feedback signal will be in phase with the input. That's the basic requirement for the oscillators. Okay. This equation, Kirchhoff law, this is the Kirchhoff law. It is written for the first loop, this one. Okay, current I1 is flowing through C and R. Okay, and this is the resistance of resistor R. Capacitor gives our position. It is 1 over JC omega, right? And in this loop, current I1 is flowing like clockwise. Okay, true that it is positive, but I2 is flowing through R. I2 is flowing through R. It is, like it enters like this, along this direction. But it is going up as I1 is going down. I1 is going down mean it is positive, right? Whereas I2 is going up through R. That's why it is with negative sign. And input is V in, so right hand side is V in. Okay. Now this is the equation. This is the Kirchhoff law. It is written in the second loop. Okay. For I2, all the resistances or oppositions or impedances, they are positive for I2 because this is a loop of I2. So here three opposition, R, C and R. And R becomes 2R, and opposition by capacitor, it is 1 over JC omega, right? Now through this resistor, current I2, it is down. So for I2 this is positive, but I3 flowing through the same R, in up direction. In up direction means this is negative. Similarly, in this loop, okay, I2 is okay. This is a loop of I2, but I1 is flowing. I1 through the same resistor is flowing down. For I2 it is positive, but for I1 it will be negative. Okay. Now we are writing the Kirchhoff law in the third loop. You know, this one is the third loop. There are three elements R, C and R. There are two R, so that is here. Capacitor, that is here, 1 over JC omega. But you know, not down. For I3 always positive, but you know, as I3 is flowing up to R, okay, it is positive. But I1 is flowing down, so it is taken as negative. Okay, so there is no battery in the loop, so it is equals to 0. There is no voltage directly, same voltage, so it is equals to 0. Now we written in matrix form like I1 component is here, right? I2 component minus R. There is no I3, so 0. That's okay. Then you know, like there is I1. I1 is here minus R. So right, I2 is here. So this is the component. I3 minus R, it is here. Again, there is no I1, so it is 0. I2 minus R and I3, this one. So I1, I2, I3, and here V in 0, 0. So V in 0 and 0. Okay. We'll use Cramer's rule for finding I3. Okay, how? First we will solve this one, this matrix. Let me call it capital T. After solving it, you know, that is capital D, okay? After solving it, we'll replace this column with this column that we call D3 matrix, and then we'll solve D3, and I3 is obtained as D3 divided by D. Okay. Now we will solve for D3. This is D3, how this column is replaced with this one. Okay, then we call it D3. Alpha square equals to 6.